Let us look at this example of interference. There are two identical loudspeakers located at points A and B, 2 meters apart. The loudspeakers are driven by the same amplifier and produce sound waves with a frequency of 784 Hz. Take the speed of sound in air to be 344 meters per second. A small microphone is moved out from point B along a line perpendicular to the line connecting A and B. At what distances from B will there be destructive interference? First we redraw the problem and assign the parameters of distances r. Here we see r1 is the unknown x, r2 forms the hypotenuse of a right triangle. The length r2 can be obtained using the Pythagorean expression. We recall that for a destructive interference, the difference of the distances is a factor of n plus a half. Substituting the equations of r previously determined to get an expression which we rewrite it. Now we square both sides and obtain an expression for the distance xa or r1. Now we get the value of x if n is equal to 0. N equal to 0 would give us the least value of the wavelength that is non-zero. We also substitute the expression for the wavelength and rewrite it as the fraction of the wave speed of sound in air and the frequency of the speakers. So, when we substitute this to our general expression, we get that the value of x is about 9 meters for n equal to 0. That produces a destructive interference. You can also get the succeeding destructive interference by substituting values of n equal to 1 and so on. Here we examine the scenario for constructive interference. So, we recall the equation for constructive interference, which is a multiple of n wavelength. Substituting the equations obtained earlier and rewriting the expression. We then square both sides of the expression and substituting the expression of the wavelength, then we get a general expression for x. For the value of n we selected 1 not 0 since 0 would not yield a non-zero value for the wavelength. So we get that the value for x or r2 is about